Hello friends, in this video I'd like to solve the following problem from Lowell Putnam Mathematical Competition 2010, problem A5. Let G be a group with operation star. Suppose furthermore that first, G is a subset of three-dimensional space R cubed, and moreover, suppose that for each A and B in our group, either their cross product equals A star B, or A cross B is 0, or both. We wish to prove that, in fact, A cross B equals 0 for every two vectors AB in our group. It's a very interesting problem, rather difficult and convoluted, I'd say, but here are my hints. First, remember that this cross denotes the cross product in R cubed. In particular, for every two vectors A and B, A cross B is both perpendicular to A and perpendicular to B. It satisfies some further constraints, but whatever, we will need this fact. Moreover, remember that A is parallel to B if and only if their cross product is 0. And what is a group? Well, it's a notion from abstract algebra. A group G with operation star should satisfy the following three axioms. First of all, this operation should be associative, so A star B in parentheses star C should be equal A star in parentheses B star C. Moreover, in every group there should be a neutral element called E, such that A star E equals E star A equals just A for every A. And moreover, every element should have its inverse. That is, for every A in our group, there should be a B in our group, such that A star B equals B star A equals the neutral element. If, moreover, one more condition is satisfied, namely that A star B equals B star A, then G is called a commutative group. Okay, so, and now for the actual proof. Suppose to the contrary that A cross B is not 0 for some vectors AB in our group, then it should be pretty clear that G cannot be a subset of any line, it's not contained in any line, and then crucially prove the following three lemmata. First lemma is very general. It says that in every group, it doesn't have to be our group, in every group G, if for every two elements x star x equals neutral element, then G must be commutative. Second lemma, which is just about our group, show that the neutral element of our operation star must be 0 vector. And then the third and the most important lemma is that for every two elements of our group, x star x is 0 vector. And finally, remember that vector product, cross product, is anti-commutative. That means that A cross B equals minus B cross A. So give this problem a try, and I will see you in just a minute. Okay, so first I want to prove my three lemmata. Maybe I will start with proving my first lemma, because it's very general. It says that for every group, if this is the case, then G must be commutative. So let's prove it. Proof of my first lemma. It's rather simple proof, since this condition is satisfied for every element x star y star x star y should be a neutral element for every x and y. Okay, but now I know that my operation is associative, so I can put parentheses in different order. I can put it in that order. And now what I will do, I will take both sides and make it star y. Okay, and what happens now? Well, I have the following. x star y star x star y star y equals e star y. Okay, and now let's see what's happening. Well, here I have x star y star x star y, or maybe, sorry, I will put parentheses in different order. I will put y star y here. And and remember that E is neutral element of our group. So E star y, it's just y. Okay. Again, by our assumption, this quantity right here, it's just E, our neutral element. But again, if I take star with my neutral element, I can just omit it. Okay, so now what I will wish to do is to take star x on both sides. And now I have the following: x star y star x star y equals, star x equals y star x. And now again, one last time, I will put parentheses in different order. And let's notice that x star x is again, by our assumption, its neutral element. And again, taking our star operation with neutral element, it's just x star y. So x star y equals y star x, which exactly means that our group is commutative, because it holds for every two x and y. That implies that G is commutative. And that closes our proof of our first lemma. It was a very general lemma. Okay, very well. Now, I wish to go to my main problem, and I was supposed to the contrary, going back to our stated problem. Suppose to the contrary, let's suppose to the contrary that what happens, that x cross y, or maybe a cross b, let's say, that a cross b is not zero for some elements, a and b in our group. Okay, that means that G is not contained in any line. Again, why is that? Well, if G were to be contained in some line, then every two vectors would be parallel. And we know that cross product of every two parallel vectors is 0. And we suppose that it's not 0 for some vectors. Okay. And now I wish to prove my second lemma. And also I will need some pages. Very well. My second lemma says that the neutral element of my group is just 0 vector. Proof. Again, I will prove it supposing to the contrary, that, let's suppose to the contrary that it's not the case. that E is not 0. Well, that means since our vector is non-zero, since E is not 0, and since G is not contained in any line, we can deduce that there must be a vector, let's say X in our group, such that X is not parallel to E. Again, why is that? Well, if every X were to be parallel to E, then again our group would be contained in a line. Okay, and now that means that X cross product E is non-zero. Very well. But since this is not zero, by the formulation of our problem, that implies that X cross E equals just X star E. And E is just a neutral element of our group, so it's just X. And now we have a problem. It's a problem because we know that X cross E is perpendicular to X. It's a contradiction. It is a contradiction because X cross Y is perpendicular to X, so X cross E cannot be equal X because we are dealing with non-zero vectors. And that's a contradiction, which means that it must be the case that E equals 0, in fact, and that closes the proof of our second lemma. So now we know that the neutral element of our group is, in fact, 0 vector. And now the third and most crucial lemma, lemma number 3, says that for every vector G, vector X in our group G, X star X is in fact a 0 vector. And I will prove it. Again, I will prove it by the way of contradiction. But maybe let's first notice that if that 0 star 0, well, we know that 0 is exactly the neutral element of our group, and E star E, it's E. But again, E is 0. Let's write by lemma number 2. Okay. And now let's suppose to the contrary. Again, as you can see, a bunch of times we suppose something to the contrary. Suppose to the contrary. Or maybe, you know what? No, let's do something else. Let's take just any non-zero vector. So we are taking X, which is in our group G, but non-zero. Well, since G is not contained in any line, there must be another vector, non-zero, in our group, such that X is not parallel to Y. Very well. And now I will define the third vector. Let Z, maybe I will write it in green, let Z be just the cross product of X and Y. We know that z is non-zero because we are taking two non-zero and not parallel vectors. We know that cross product of two non-parallel vectors is non-zero. So let's write it. Since x is not parallel to y, it must be the case that also z is non-zero. Z is non-zero, and also z is perpendicular to x because it's a cross product of x and something. And I will show, we will show first that x star x must be parallel to z. How can I prove it? Well, suppose now to the contrary that it's not the case. Suppose to the contrary that, well, x star x is not parallel to z, i.e. X star x cross product z is non-zero. What can we do from that? Well, let's take a look. X star x cross product z. Since we know that this cross product is not zero by one of the conditions of our problem, we can change this cross product to star operation. Okay, and now because we know that our operation star is associative, we can put parentheses in the following order. And now finally, notice that x and z are perpendicular and non-zero. Both are not zero. So we know that their cross product is also not zero. So that means that cross product of x and z is non-zero. And since this cross product is non-zero, I can change my star operation. Or maybe yes, I can change one of my star operations to cross product. And moreover, let's notice that x cross product x cross z is also non-zero because we are taking a vector non-zero and another non-zero vector which is perpendicular to it. So their cross product is also non-zero. Okay. And now I'd argue that we have a problem. Why? Notice that this vector right here, x cross z, well, it's obviously perpendicular to x because cross product of two vectors is perpendicular to both of them. So it's also perpendicular to x cross z, but let's also notice that this vector equals some vector cross z. So it's also perpendicular to z. And now it's a problem because x, z, and x cross z are three perpendicular vectors in a three-dimensional space. And there is no vector which is perpendicular to three vectors which are perpendicular to each other. Apart from zero vector, but we know that this vector is non-zero. So it's a contradiction. In red. Contradiction, since in R cubed there is no non-zero vector perpendicular to x, z, and x cross z. There is no such vector. Okay, and let's take a step back. That exactly means that I have demonstrated that x cross x, x star x, sorry, is parallel to z. So in other words, if x is perpendicular to z, then x star x is parallel to z. It's parallel to z. Very well. But now let's also notice that x is perpendicular to z. Moreover, x is also perpendicular to x cross z. Why is that? Well, again, by definition or by property, x cross z is perpendicular to both x and z. And by making the same reasoning as above, literally the same, apart from changing z to this vector, we can demonstrate that in the same vein, x star x is also parallel to x cross z. And that's a problem. Not exactly. That means, maybe let's write it in pink. That means that x star x must be in fact equal to 0. Because this vector and this vector, they are perpendicular. And the very same vector cannot be parallel to two perpendicular vectors. It can be in only one case, if it's 0. So it must be 0. And that closes the proof of our third and final lemma. Okay. After all of that, first of all, I need a new page because I'm running out of space again. Perfect, I have a new space. So we are done with our lemmata, and now by lemmata 1, 2 and 3, by lemmata 2 and 3, we know that for every element x in our group, x star x equals the neutral element. Again, why is that? Because we have demonstrated in lemma 3 that x star x is 0, and in lemma 2 we have demonstrated that e is 0. And that means by lemma number 1, we know that G, our group G, must be commutative. It must be commutative. Let's go back. Why is that? Well, it's exactly the statement of lemma 1. If for every two elements, if for every element x, x star x is neutral element, then G must be commutative. So we now know that G is in fact commutative. And now we will just in a minute we'll get a contradiction. Maybe I will write i.e. for every two vectors of our group, their order can be exchanged. And now we will have a contradiction, because by assumption, maybe I will write it in orange. By assumption, we have assumed that there are two vectors A, B in our group such that A cross B is non-zero. It was our assumption for the lemma to the contrary, yes? That means that B cross A is also non-zero. Well, because this vector and this vector, there are opposite vectors. So if one is non-zero, the other one is also non-zero. Okay, and that means let's combine all of our knowledge. A cross B, since this is non-zero, we know that it's A star B. Since our group is commutative, it's B star A. And again, since B cross A is non-zero, it's B cross A. But remember that a cross product is anti-commutative, so B cross A is minus A cross B. And let's take a look. A cross B equals minus A cross B. And that means that only one thing, A cross B must be equal 0, and now we get a contradiction, because we have assumed that A and B, their cross product is non-zero. So it's our final contradiction. It's our final contradiction. So our mistake was to assume that there were two vectors whose cross product is non-zero. There can't be. There can't be. So let's write our final conclusion and let's finish this off. So that means that for every vectors A and B in our group, A cross product B must be equal to 0, and that closes our proof, because we wanted just to prove that. Okay, so as you have seen, a very convoluted problem, a lot of lemmata needed, but I'd also say that it was pretty nice, because it was pretty algebraic problem, combining both linear and abstract algebra. And that's it. Thank you for watching, and I will see you next time. Goodbye.